Hello. The purpose of this video is just to make sure that you have an overview of the big ideas from the probability distributions section chapter of the IB curriculum. A lot of this stuff is, in my view, a little bit simpler than a lot of the other content we have studied. And however, it can get tricky. So it's something where you want to take it slow and make sure that you are paying close attention to the different definitions and when it is appropriate to use each of the tools. Because once you know which tool to use, the process is fairly straightforward. But if you're using the wrong tool, you're going to get the wrong results. So, big picture, probability distribution come in two different flavors. There are discrete probability distributions, and then there are continuous probability distributions. Everything that we know um, about probability can be applied in one of these two situations. And then, very basically, discrete just means there's a certain set, a finite set of possible outcomes. Usually, this is a small number of possible outcomes. Like if you're rolling one die, there's only six outcomes. If you're flipping a head or tail, if you're flipping a coin, heads or tails are the two different outcomes. I nailed that one. And that's different than continuous, where it could take theoretically an infinite number of outcomes. So things that, like, how long does it take for something to happen could theoretically take an infinite number of outcomes, depending on how precisely you measure the value of time. Or what number could this function produce? That's a continuous example, because most functions, like an x squared function, would produce any number of values. So discrete means there's only a few finite values that can be attained, and continuous means there's a range, an infinite number of values within a certain range that can be obtained. But here's the biggest thing that is true, is that the probability of everything happening, the probability of something happening in the universe of possibilities is 1. Something will always happen in your probability distribution. So the probability of the universe is equal to 1. What that means in a discrete situation is that if you sum up from all of the different possible events, so from k equals 1 up to n, the probability of something happening, your random variable, which we usually use a capital X. So the probability that your random variable, the probability that something happens. So a lot of times you'll see this sort of notation here, where you have a capital X and then you have a lowercase x. What that's saying is the probability, capital X is all the possible things that could happen, and then xk is just one possible thing that could happen. So in the example of flipping a coin, capital X would mean what are the two things that could happen, heads or tails, and then you'd have an x1 and an x2, heads and tails. If you were rolling two dice, then capital X are all the possible combinations that could come out, and then you'd have all the different possibilities. XK could just be like the sum of the dice is 2, the sum of the dice is 7, and in that case, all of the different possibilities would be getting from a 2 up to a 12. The idea here is that if you add up all those probabilities, you're going to get an answer of 1. I know sometimes it's a little weird at first. You see an equal sign inside the parentheses and an equal sign outside the parentheses. The equal sign inside the parentheses is saying that you get a certain event, and the equal sign outside the parentheses is saying what's the probability of that thing happening. And here I'm saying that if you add up the probability of all the possible events, you're going to get 100%. You're going to get 1. Well, with continuous, you're not going to be able to add up all the possible events because there's an infinite number of them. You could have x equaling 1 or 1.1 or 1.72 or 1.073. So there's always more events than you could possibly add up. But luckily, we know that integration can add up a continuous valued function. And so here, what we're saying is that the integral over all possible values from negative infinity to infinity of our probability distribution function is going to equal 1. Now, in practice, these numbers here are almost never going to be negative infinity to infinity. They're usually going to be just like some a value and some b value. You're going to get a probability distribution function that's only defined for certain numbers and then isn't defined outside of that. And so usually we'll be able to replace those with like from 2 to 7 or something like that. In theory, it's possible for a probability distribution function to extend infinitely in both directions, but usually in the problems you're going to be doing, there are two set values that you're going to integrate between. Okay. In discrete distributions, you have a thing called the expected value. It's the same thing as the mean. It's what's the average outcome? What do you expect to happen here? And we use the Greek letter mu for that. And that comes from doing the sum again over um, all your possible values. And then what you're doing though is you're actually taking the outcome itself, the value of the outcome itself, and you're multiplying by the probability that you reach that outcome. Sorry, my pen is tripping out on us. So what we're saying here, we have a capital X on the inside. I might need to abandon this if this is going to be annoying like that. So we have a capital X equals little x. So what we're saying is take each of the possible outcomes and multiply it by the probability that that outcome happens. This is like, for example, if you're playing a game and you win a different amount of money depending on the number that shows up on the dice that roll. You roll 2 dice, and you get different amounts of money. And so what you're doing is you're taking the amount of money that you win and multiplying by the probability that you win that amount of money. And if you add up all of those possible outcomes multiplied by their probabilities, you'll get your average expected value. And what that means is if you were to play this game a large number of times, on average, how much do you win per time or lose per time? If you use this calculation in the context of like a casino, you'll see that your expected value is always negative. The casino, on average, will win money. So from when people say the house always wins, another way to say the house always wins is the house always has a positive expected value. Very similar definition for continuous. You have, instead of a sigma for sum, you have your integral symbol from negative infinity to infinity of x multiplied by your probability distribution function. Great. Oh, come on. There you go. Just got to be a little more. Okay. And then the last thing that I wanted to cover here was that the variance, sigma squared. This comes into play when you're looking at how variable a distribution is. In other words, how spread out is the distribution? Is it tightly clustered around one or two different values, or could it really just be a lot of different values? So the variability of it can be measured with the variance. There's a couple different definitions that are equivalent to each other. So one definition, probably the most straightforward definition, is you're doing the sum again from k equals 1 to n. And what you're doing is you're seeing how far away is each of my values from the mean. So this should say n on top. I'm taking each of my values, each of my xk's. I'm saying how far is it away from the average, from mu. And then I'm squaring that and multiplying by the probability that we achieve that particular value. So what's going on here? Subtracting tells you how far apart they are. Squaring makes positives and negatives count equally towards your variance. And you're multiplying by the probability because you want to count things that happen more often as a higher count towards your variance. So that's what the idea there is. Very similar idea for your continuous probability distribution. And there's a reason we're using sigma squared, by the way. Many of you are probably more familiar with the idea of standard deviation. Standard deviation is just sigma. So if you calculate the variance, just take its square root and you will have it. Okay, so given that my pen is kind of tripping out and the video is already getting long, let's call it right there. Every situation that you encounter in the IB curriculum, your first question should be, is this discrete or is this continuous? And that'll let you know, are you going to be adding up every single possibility with a sum, or are you going to be integrating your probability distribution function? And are you finding the probability of a certain event happening, or are you finding the expected value, or are you finding the variance and then using the correct formula for that situation? In the other video, in the next video, I'll talk about two specific types of probability distribution situations that you're expected to know. One discrete type is called binomial distribution, and then the continuous type is called normal distribution. Okay, so thanks for watching. Let me know if you have questions.